Okay, so solubility is a topic that we did in grade 11, and we did a variety of calculations. So you did in grams per milliliter, and we did solubility curves, um, and we also you would have thought about this, without even thinking about the chemistry behind it. How much can you get to dissolve in something else? If you are making a solution in your home, say if you're trying to dissolve sugar in your coffee or tea, all of those kinds of things are solubility. So we're going to look for specifically solubility should apply to an amount. And so again, because we're going to do ice tables and we always want to put concentration in the ice table, then we are going to focus on what we call molar solubility. So not necessarily the similar units to density like we would have done in grade 11, like grams per liter. We're going to focus on moles per liter. So last year we also talked about the theory behind solubility. So solids increase in solubility as temperature decreases. Most gases decrease in solubility. But we are really going to focus on solids. So last year we would have used a chart and decided whether something was insoluble or not. So this year we're going to sort of say, well, what happens if we can force these insoluble substances to dissolve? So that's really what we're going to do this year. So these numbers are going to be tiny. So I sort of alluded to that before. You have to really get to know your calculator and make sure that you can do scientific notation. Because these numbers are so small, you won't be able to change them into decimals and in a useful way in your calculator. It just won't hold that many zeros. Okay. So last year we switched the partners to figure out what the solid was. Even in grade, your grade 10 teacher might have made you do it where it was a double displacement reaction. Some tricks to it to keep, say this one here, this nitrate, to keep that together. For double displacement reactions are actually the easiest to balance, that kind of thing. So last year, one of the topics was that we had to write the total ionic equation where we split apart everything. That was aqueous. Then we did the net ionic equation, which showed the formation of the solid. So you could cross out the spectator ions. So nitrate is aqueous on both sides. So is sodium. So chemically, when you do this, nitrate is a very soluble, very small ion. So it's a polyatomic ion that you often see in formulas, and there's a reason for that because it's so small, easy to dissolve. That's makes it a nice aqueous solution, which makes it a little bit more reactive, which of course we like, right, as chemists. Same thing with table salt, easy to get, right? So yes. They're aqueous on both sides, so they're spectators, they don't change. Aqueous, aqueous. Sodium's aqueous, aqueous. So then the net ionic, so we wrote out total ones, which are fine, but it doesn't really show us the formation of the solid. So even as a grade 9 student, we would have said, what's one of the signs of a chemical change? A new substance or precipitate is formed, right? So that is what makes, that's chemistry, right? What's the precipitate forming? So you just take the ions from the solid and make the equation. So in grade 11, students are often frustrated. How do I remember what the charge is? So you can use your periodic table. You can uncross like this. The number here, which is a 1, would have come from silver, that kind of thing. Metals are always positive. Non-metals are always negative. The substance written in any formula that's written first has a lower electronegativity. So that means it's going to be positive. So there are a bunch of ways to remember, but really at the least you could look it up. So if you choose to use our periodic table, then for transition metals, the charge is written underneath. For chlorine, which is one of the ones where you can just count the columns and find its charge, your textbook, I think for transition metals, it writes it on the right-hand side of the symbol. So different periodic tables have different formats, but transition metals are more difficult to predict, so you have to be given it, okay? So this is net ionic. What we're going to do now when you have, because we're going to do equilibrium, so there is a considerable amount of reversibility, which makes sense because last year we would have said, no, this is a solid. Now we're going to take the solid and dissociate it into ions, okay? So solid is always the reactant. I'll give you what the formula of the solid is, but you have to be able to split it apart into ions. You should use the double arrow. Okay, so always you're given what the solid is and you split it apart into ions. Eventually what we're going to do, because it's equilibrium, we are going to write an equilibrium law. So the charge doesn't necessarily matter, okay? However, depending on what the formula is, there could be coefficients out front, which then of course become the exponents. So you do need to pay attention to that, okay? So we'll do a couple of examples. In a minute. All right, so like I said, last year you would have qualitatively said that silver is insoluble, but now we're going to force it to dissolve. So by definition, an equilibrium is established when you have a saturated solution. So sometimes it'll talk about solubility, sometimes it'll talk about saturated solution. So you need to remember that a saturated solution means that it's at equilibrium. So when we build the ice table, saturated solution values, concentrations, go in the E line. So yesterday it was a little bit more straightforward. So initially we have this, at equilibrium the concentration is this. This time it will use words like saturated solution or molar solubility. So I actually kind of snuck one of these equations on the first worksheet where you were originally just practicing like writing the equilibrium law, don't include the solids, that kind of thing. So when you do these questions, the solid is always going to be the reactant. I forgot the chart there, sorry. And then the products are always going to be ions. So what that means is if you have the K is products over reactants, then if the reactant is always a solid, there is never going to be a bottom of the equation. So in a way, these are a little bit simpler. You're just multiplying. You don't have to worry about trying to rearrange with the division. So that's just a principle, like I said. I think it was actually AGCL as well. I just kind of snuck it in there. So no solids. So even when we write our ice table, we're going to cross it out. So the equilibrium law, if it's products over reactants, because the coefficients are going to come from the formula, and really, you can't have, there's no charge higher than 3, right? So there's never going to be, it's either 1, 2, or 3. It's not even that much variety. And then instead of KQ, we write KSP. But it really doesn't matter. It's essentially the same thing. S for solubility, P for product, because we're always going to be just multiplying, and the answer to multiplication is called a product. Yesterday we had quotient because it was going to divide, but we're never going to have a bottom because it's always going to be a solid on the left or in the reactant side. So you'll either be, it'll talk about concentration in a saturated solution, or you can be given molar solubility. So molar means we're going to focus on moles per liter, or big M. Just like the ice tables we did yesterday, you don't put moles in them, right? And then, so these molar solubility values also, if you're given that, they should also go in the E line. If you want to write that down here. So it's like we're saying, okay, initially we have solid, we have no ions, and then we let it reach equilibrium. At equilibrium, what is the concentration of the ions? Okay, so the first example we're going to do is just writing the equilibrium law. So basically I did one that has a 2, one that has just ones, and one that has a 3. And really that's it. There's not a lot of variety because you can't have that many different charges. Okay, so the first one, again, never including the solid, we have silver with a coefficient of 2, so it becomes its exponent. And then CrO4. Okay, so this, if you hate polyatomic ions, sometimes students get muddled up by the charges, okay? So similar to anything that you've ever balanced or whatever, this charge has no effect on what goes in the equilibrium law. Actually, don't highlight that one. Highlight this one. So you want the coefficient to become the exponent, just like we did before, okay? The charge, we don't even really care. Yes, it should be there. Aqueous means ions. Ions have to have charge. But if you find that it just screws you up, don't even worry about it, okay? The coefficient is what makes the exponent. It's way more important. So down here, for B, there's nothing written out front, which means that their exponent is 1. So you can choose to write the 1 or not, just like we've been doing before. It's up to you. But if in your note you want to emphasize that it's 1 because the coefficient is 1, and then C, this time now the silver has a coefficient of 3. So I won't make you write the formula of the solid. I'll give you that. You don't have to worry about crisscross rule and all that kind of stuff. However, you do have to be able to split it apart into its ions, okay? So you have to be able to write a dissociation equation. Okay? So there is really 2 types of questions. You're either going to calculate the K value or you're going to calculate the concentration. Similar to what we did yesterday, except it's even easier because there's never a reactant. So you don't have to use the quadratic formula. You don't have to worry about trying to bring a binomial that has an X value in it up to the top. So the math here is a little bit more straightforward, except usually the numbers you're going to be given are scientific notation, okay? So find your EXP button on your calculator or whatever. Make sure that you get to know it so that you don't make annoying math errors, okay? This is also a case too where, because my calculator is easy to switch between scientific notation and not, then my answer might be rounded a little bit different than what you get, and that's totally fine, okay? So it says the molar solubility of AgBr in pure water is 7.1 times 10 to the negative 7. So it does not say that that value goes at equilibrium like it did in the other questions. So when you see molar solubility, you have to be thinking that's the maximum amount that's going to dissolve. Where is the saturated solution going to be? Equilibrium, okay? I've give you what silver, bless you, silver bromide is. Put the solid on the left and split it apart. Then we do ice because we're trying to find KSP. So this question, sometimes students kind of beat the system and try not to write an ice table, but usually get marks for it. Okay, so show all of your work. And it's really straightforward. So if you do so topic number 1, I forget how many questions are there, but even if you do a couple of them, it's the same thing over and over again, okay? It's not very hard. Cross out the solid because we don't include it. And then remember, it's like we would have said this is a solid. So initially, we have no ions. Then the solid has to increase because these are 0, or the ions have to increase. Can't go down from 0. So the same principles apply. Wherever the 0 is, that's where you put the positive. If there was a coefficient of 2 here, make the x 2x or whatever. But most of the time, it's either going to be 1 or maybe a 2, maybe a 3, but that's even more rare, okay? So we have 2 options. Do we know what x is? So what we're going to kind of do is cheat a little bit at stoichiometry. Technically, it says the molar solubility of AgBr in pure water is 7.1 times 10 to the negative 7. Technically, this is AgBr, yes? So that value should go here. However, we don't care about the solid because it doesn't affect the equilibrium. But logically, if this is 7.1 times 10 to the negative 7, these two will be the same because it's all 1 to 1 to 1. So you could do stoichiometry. You could do the ratio thing. So what's the concentration of Ag? Its coefficient is 1. If AgBr, its coefficient is 1, and what would you get? You would get the same thing. Okay? So we kind of, I'm not going to say cheat, we streamline stoichiometry. And so if this is a coefficient of 1, and the solid always should be, okay? Then, and this has a coefficient of 1, and so does this, they're all going to be the same. So the next one, when we do lead, silver chromate, lead 2 iodide, there'll be a coefficient of 2. So it's very, very straightforward. We can always sort of streamline it, but this is what you're kind of thinking. If they have the same coefficient, then their concentration is the same. And that's why we don't use grams per liter anymore, because you can't do stoichiometry with grams, right? Only moles, or moles per liter, only concentration. So even though in grade 12 we don't focus a lot on, finding the number of particles, Avogadro's number, it's still always in the back of the mind about moles. 1 mole of something has 6.02 times 10 to the 23 particles. So you can compare moles because that's a similar unit for every kind of amount. Whereas grams is how much space something takes up. So a mole of gas and a mole of desks would not be the same in grams. Okay, so KSP, so you get marks for ice tables, you get marks for writing the equilibrium law. Since they are the same, you could write that as 7.1 times 10 to negative 7 squared. That's fine. Again, this is really just making sure you don't make a calculator error, which is very annoying. Oh, wait, maybe. No. Yeah, I don't know. Sorry. Yeah. Okay. So this question is very similar, except this time it's Ag2CrO4. So still says molar solubility, still says find the KSP. You do the same thing. Put the solid on the left, but this time now we have 2 silvers. So if you are frustrated by polyatomic ions, then that's where you need the back of the periodic table, okay? Because they're on there, chromate's on there. The only polyatomic ion that's positive is ammonium, and ammonium will never be part of a solid. It's very soluble. So really also the metal, there will only be one of them, like Ag, MgCa, whatever. So then the polyatomic ion would only be the second part. You can also think of it that way for this because the only polyatomic ion that's positive is ammonium, which is very soluble. It would never be in one of these in a solid form. Usually they're transition metals, like lead is a big one, silver, sometimes calcium, depends what it's bonded with. So we do the same thing. Ions start at 0. However, this time now with silver, because of the coefficient of 2, then it becomes 2x. And the same thing when you have the molar solubility of this, These two are the same because they have a coefficient of 1. But the silver, you're just going to multiply by 2. So again, you can think of the ratio. So what is silver? Its coefficient is 2. This coefficient is 1. And basically all you're doing is multiplying by 2. So here, or this 2, if this is x, then you're just multiplying by 2. So the simplicity, it almost seems too good to be true. So for this part, the basic solubility problems, it really is this simple. No ions to start with. You're either given the X value, the molar solubility, or the concentration in a saturated solution, or the next kind of example, we're going to be given the KSP, and we have to solve for molar solubility. But again, it's not going to be as tricky even as yesterday. So now we have this 2 here, which means we have to square it. I didn't say it out loud, but I forgot. So similar to the other K value, the KQ, there's no units. Okay, so I'm not going to worry about moles per liter inside the brackets because it doesn't matter. So you decide for yourself if you can do this all in your calculator as one step. If you need to show more than one step, you do whatever works for you. You should get 1.2 times 10 to the negative 12. So really, really tiny values because again, last year we would have said, nope, these cannot dissolve. Now we're forcing them to dissolve, so it makes sense that it's just a little bit dissolving. So this time it says calculate the KSP of lead iodide dissolving in water if the concentration of lead ions. It doesn't talk about molar solubility. It talks about what the concentration is. Same thing. There's 1 lead ion and there is 2 iodide ions. And we still do the same thing. Write the equilibrium law. times the value by the concentration value by 2, also square it. I believe this is definitely one I think that rounds different if you don't have a calculator, or if your calculator puts all the values, the zeros out instead of scientific notation. And I don't care if your calculator gives you an answer that's not scientific notation, you can just leave it like that. Is that it? Okay. So then the last kind of question you could be asked is, this time now we want to find molar solubility. So we have to solve for x. Given the KSP, so similar to yesterday. And I chose PBI2 because it has a 2 in it, which is the most complicated kind of question you could get here because we have to do the cubed root. So again, you know, this year, based on your limited math, then that's as far as we're going to go. You'll either have just a squared term and you can just square root, or you'll have a cubed term and you have to cube root, okay? So it tells you lead iodide is the solid. So now you're given the KSP. So sometimes students will put this value in for X in down here, but you have to, it says the KSP is, or whatever, has a KSP of, and the KSP goes on this side, right? So now this time, we don't know what X is, so we have to solve for X. Similar to yesterday, you can write it, if you prefer to write it, it's like I plus C. You can do 1, or sorry, not 1, 0 plus X, but that really, we ignore the 0, right? So, but you can write it in there. It's not going to affect anything. The 0 doesn't do anything, but we're doing, and we're going to always have zeros, right? So, because we don't have any ions to start with. So this is where we're going to get, this is X. 2x squared is 4x squared. So you do have to remember when you multiply a common base, you add the exponent. You can do this math all as one step in your calculator too. But again, if you don't have a good relationship with your calculator, I would do it in steps. Okay? So you divide by 4 first. And then to get rid of cubed, you have to do like the cubed root. I'll do it in a different color. So some calculators have a cubed root button. Some of them, it's got an X and then the square root sign. So you have to put the 3 and then push that button. So again, you really kind of have to know your calculator. Your answer button might be helpful here. Use scientific notation or not, I don't care. But you want to be careful with your final answer. These problems pretty much solve themselves, except you have to think about what x is, and you have to make sure to answer the question, okay? So again, here your calculator might have given you 2 times 10 to the negative 9. It doesn't, if you can't switch between them, it'll round, that's fine. But you don't, similar to yesterday, you don't just want to leave x because the question asks us for molar solubility. So technically, that should be in moles per liter. So you can either make your x value and make sure it has units or write a sentence. You can do it all as one step. I don't mind.